Okay, good morning, and we will start sharing the screen soon. Yeah, so I hope you can see the screen. This is the result which we had proved last time. We had found the probability density function of W1, W2, the two-dimensional random variable. This we had proved. Yeah, and using that PDF, we want to get hold of the PDF of A1, A2. So the sum of the steps involved is going to be given as exercise, fairly simple. So we know that A1, A2 can be expressed in terms of W1, W2 like this. So this suggests that the linear transformation is given by this matrix. So let C denote this matrix. So 1 and 0 in the first row, minus 1 and 1 in the second row. So clearly the determinant is 1 and C is a non-singular linear transformation on R2. So that is easy to verify. And this is a good exercise for you. You should prove that this transformation C maps the region G2. G2, remember, is this region. W1, W2 takes value here because W1 will be less than W2 and both are positive. So it will take, and both are finite with probability 1, that is less than infinity. So G1, W1, W2 takes values in this G2. And of course, A1 and A2 are both are positive. So one expects A2 to take value here in the positive quadrant. So C is the transformation which maps this G2 onto this H in a 1-1-on-2 fashion. Remember that the PDF of W1, W2 is 0 outside of this region, outside of G2. And we also expect that the PDF of A1, A2 would be 0 outside of this positive quadrant. Note it down. So such exercise, please do not neglect. You always, when you are dealing with especially 2 or higher dimensional random variable, the random variable concerned might not take all the values in that appropriate space, Rn or R2 or whatever it is. It might be taking values only in a region. And very often we may come across regions like the half plane or half space or quadrant or orthant or this kind of triangular kind of regions, G2. Okay, please note it down. So it's inverse. So since it's a non-singular transformation, it has an inverse, and you can easily check that this matrix, C 1 and 0 in the first row, 1 and 1 in the second row, is the inverse. And we have agreed that generally we will, when we talk about vectors, we mean column vectors. So this A1, A2, that column vector is the image of C, I mean the image of W1, W2 column vector under C. And of course, when you apply this C inverse to A1, A2, the map you get W1, W2. So that in terms of A1 and A2 is expressed here. It's very, all are very simple. Please note it down. Almost every step is elementary, but only that is a collection of a lot of elementary steps. Okay. So now this is the result. The two-dimensional random variable A1, A2 has the probability density function. So that density evaluated at A1, A2, if A1 and A2 both are strictly positive, then it is lambda times e to the power minus lambda A1 multiplied with lambda times e to the power minus lambda A2. And it is 0 outside. So this expression we denote by bullet with a subscript 2. 2 for the two dimension. And this means that the random variable, this is the product of the density, because here you also see that this is a kind of a rectangular region. So there is no difficulty in seeing this is a product of two densities, two one-dimensional densities. And as you had guessed in the last class, A1 and A2 are independent and each of them has a exponential distribution with parameter lambda. And we already know that A1 has an exponential distribution with parameter lambda. Please note it down. Okay, the proof is now simple. Now that all the hard work was done in getting hold of the probability density function of W1, W2. So in view of that preceding exercise and the earlier that theorem concerning change of variables, which is in the first set of notes, Poisson process 1. So F sub A1, A2 at little A1, A2 is F W1, W2 evaluated at this point. So this is that C inverse of A1, A2. So at A1, comma A1 plus A2. And from that previous result, we have this is equal to this one, as long as these two are non-negative for positive. So that would make A1 strictly less than A1 plus A2 and both are greater than 0. So this point for A1 and A2 strictly positive, note that it belongs to the triangular region G2. So this is lambda squared times e to the power minus lambda A1 plus A2. So that obviously splits like, can be split like this. So of course, outside of this quadrant, this is 0. So completes the proof. In some of the books, you will see proof of this using some intuitive reasoning, but yeah, well, since this can be presented without bringing in too much machinery, I thought I will do it this way. First going to W1, W2, and from there getting. Probably this reasoning, this kind of way is also given in quite a few books. I mean, no originality is claimed here. Okay, so the two-dimensional case we have taken care of. Now we will go to the n dimension. Please note it down if you want. So in the n-dimensional case, we are going to sort of imitate this procedure. So conceptually, it is not that difficult at all. It is just that the notation becomes a bit more complicated. So as we have done in the two-dimensional case, we will first look at W1, W2, Wn. What I would suggest is to get a kind of hold on this thing. You try to do it for W1, W2, W3. N equal to 3 you can take and try to write it. I mean, after seeing this in your own words. So in the case of two-dimensional random variables, we saw that W1, W2 takes value in G2. So in the corresponding object in the n-dimensional case is going to be this, what we have denoted by Gn. Note that W1 will be, I mean, all these guys are positive. W1 would be strictly less than W2, strictly less than W3, etc. Wn minus 1 strictly less than Wn. So this random variable would take value in Gn, and Gn is the region S1, S2, Sn such that 0 strictly less than S1, strictly less than S2, etc., strictly less than Sn, and all are finite, less than infinity. So as before, we consider an open set completely contained in Gn. Open rectangle, n-dimensional open rectangle. So that will be of the form A1, B1, Cartesian product A2, B2, etc., Cartesian product AN, Bn. So such a product of these sets we usually denote by capital pi, I going from 1 to n, AI, Bi. So we will see how the thing behaves when this W1, W2, Wn takes values in this n-dimensional rectangle, which is contained in Gn. And as we have done in the two-dimensional case, note that this happens. As a matter of fact, I should have put here, verify that. All the note that, etc., are exercises. So 0 less than or equal to A1, strictly less than B1, B1 can be less than or equal to A2, A2 less than B2, and so on. And Bn minus 1 less than or equal to An, which is strictly less than Bn, of course, Bn is finite. Yeah, please note it down. Okay. Proceeding as a two-dimensional case using, oh, this should be independent increments property. Yeah. So using the independent increments property and also that theorem 1, which is the basic theorem, where we found that the process which satisfies postulates N1 to N6 is the Poisson process, that theorem. Verify that. So some of the steps are skipped here because we are going to proceed as in the two-dimensional case. But since you are already familiar with the two-dimensional case, just indicate the main steps. So probability W1, W2, Wn belongs to this open rectangle contained in Gn. So since this rectangle is completely contained in Gn, we have already seen this. So which means if W1, W2, Wn is going to take values here, W1 would be between A1 and B1, W2 will be here, A2, B2, and Wn minus 1 will be between An minus 1, Bn minus 1. And Wn will be here. And any part of that this thing which is left uncovered here outside of this, that time points, their things would be 0. Of course, in the last one, Wn is going to be here, but that does not preclude the possibility or does not exclude the possibility that Wn plus 1, n plus 2 can also be here. Such a reason we also saw in the two-dimensional case. So that this event is same thing as the Poisson process n at A1 is 0, nb minus na1 is 1, and between A2 and B1 only no arrivals, and so on. Between A2 and B2, there will be exactly one arrival, and all these things. nbn minus na1 is exactly 1. There should be another parenthesis here. Yeah, some parentheses are missing here. Yeah. Please put the appropriate number of parentheses so that this makes proper sense. And nan minus nb minus 1, n minus 1 is 0. And the last interval, an, bn, there is at least one arrival. And using the independent increments property, you can write this probability as the product of this individual probabilities. Probability NA equal to 1, probability NB minus NA equal to 1, etc. So, and you will get this. Of course, you should also write B1 minus A1 as integral from A1 to B1 ds1. So if you do that, you will get this integral in the n-fold rectangle here. This is the integral over here. So that is lambda to the power n, e to the power minus lambda sn, dsn, dsn minus 1, ds2, ds1. Of course, I have commented here, as one needs to write this guy as this bi minus a as integral dsi over a1b. Please note it down. I would very strongly recommend you do this for n equal to 3, 4 and things like that to get better control over this argument. It's very simple. Conceptually, it is very simple. But when you are coming across this kind of thing for the first time, it is better to take simple cases and do it, and then you get a better grip over it. Note it down, please. Note. So as I had mentioned here, one needs to write bi minus a as integral ds, integral over a1 b1. So as before, since rectangle contained in Gn, completely contained in Gn, generate the Borel sigma algebra, one can conclude from that this is the PDF of this random variable. Of course, if one is not familiar with measure theory, you can take it that if you can express the probability that this random variable taking value in a rectangle of this form, contained in this rectangle, contained completely in Gn, is equal to this function integrated over that rectangle, then that is tantamount to saying that this function as a function of S1, S2, Sn is, of course, given to be this on this region G2, Gn, and 0 elsewhere, is the probability density function of this random. Just like in one-dimensional case, if you can write probability of the random variable taking value in an open set AB, if you can write it as integral a to b of some function, that function is the probability density function of that random. Because there in one-dimensional case, if you from the open interval, you can immediately get that integral minus infinity to x of that integral is the distribution function. So then appealing to the definition of what is meant by density function, you immediately get that. But here, that kind of argument is more involved. So that is why one takes recourse to measure theory. Especially if the region concerned is not a nice region like a rectangle or triangle and things like that, you will have difficulty in comprehending the multidimensional argument. Even for things like circles or ellipse, regions like, or some kind of an irregular figure, but which is otherwise nice. Maybe even a polygonal region and things like that in 2 dimensions. Yeah, the result is this. the n-dimensional random variable, which we should denote by W underline, W1, W2, Wn, has the probability density function F sub W underline S1, S2, Sn is lambda n times e to the power minus lambda Sn if 0 strictly less than S1, strictly less than S2, and so on, strictly less than Sn, all are finite, and 0 otherwise. Outside of this region, it is 0. So this display we denote by O dot sub n, since it is an n-dimensional object. Small exercise for you. Show that the integral of this guy over that region is 1. So that you are completely convinced that the probability of the random variable W1, W2, Wn taking value in Gn is 1. Note it down. Okay, now we want to imitate the same kind of thing which we did a few minutes back in the two-dimensional case. So to sort of go back to that, yeah, here we were trying to get, yeah, we had this expression. So now we have W1, W2, Wn, and A1, A2, An. So by the very definition of the interarrival times, you know that AK is Wk minus 1. So this kind of only thing suggested that we take C as this. And since AK is going to be Wk minus Wk minus 1, in the n-dimensional case, we expect this kind of a pattern to repeat. It will not be a lower triangular with a matrix with all the diagonals 1 and all the off-diagonal lower thing equal to minus 1. That is not we want. The main diagonal will be 1. The diagonal just below that, that will all be minus 1. That will give you Wk minus 1 kind of. So based on that simple, in the 3 by 3 case, you will immediately see that. So that is another reason why you write it out in the 3-dimensional case and probably the 4th dimension also. Okay. So now we want to get hold of the PDF of, or rather the joint PDF of A1, A2, An. So consider this n cross n matrix. It's all the upper triangular things are 0 beyond above the main diagonal. The main diagonal consists of all ones. The next diagonal here consists of all minus 1s. Rest of the entries are all 0. Please note it down. Okay. So determinant of this guy is 1. That's easy to see. So it is non-singular. And its inverse is given by the C inverse. So inverse W1 is A1, W2 is A1 plus A2, W3 is A1 plus A2 plus A3. So in this case, C inverse is this lower triangular matrix, which consists of 1 below the diagonal and above the main diagonal is all 0. So from that, actually in this case, as in the two-dimensional case, you can easily see that the inverse from this relationship, you can easily see how that C1 and C2, C inverse would be. The same kind of analogy works in the n-dimensional case. In other words, in this case, it is easy to guess what the inverse is and then check it, rather than trying to use some formula to get the inverse. Sometimes if you can get the correct guess, checking that that is the required object is easier. That's also a rigorous proof. How you guessed it, that is a different story. Their intuition might play some role, or as in this case, this is a commonsensical observation. So please verify that this guy is the inverse of C. Note it down, please, if you want. Okay. Right. So verify the following. As before, A1, A2, AN, that column vector A1, A2, AN is C applied to the column vector S1, S2, Sn. So S1, S2, Sn, that column vector is C inverse of A1, A2, AN. And from the expression for C inverse, that this thing, the form of the C inverse, you can easily see this is nothing but C inverse applied to A1, A2, AN, that column vector is the column vector given by A1, A1 plus A2, A1 plus A2 plus A3, etc., etc., A1 plus A2 plus AN. So the way you express AIs in terms of SI is A1 equal to S1, A2 equal to S2 minus S1, and so on. A3 is S3 minus S2, AN is Sn minus Sn minus 1. Yeah, note it down. So this expressing these objects in terms of the WIs and the AIs, one sees that C applied to W1, W2, Wn is this. That is your AIs. And yeah, so these things are fairly simple. Now I strongly recommend in the n-dimensional case for you to verify that the non-singular transformation C maps the triangular type of region Gn to the n-dimensional orthant. The objects corresponding in the n dimensions corresponding to quadrants are called orthants. N-dimensional orthant Hn A1, A2, An belonging to Rn such that all the AIs are strictly positive. And this mapping is one-to-one and onto. Since the PDF of W1, W2 is non-zero only in a particular region of Rn, this you have to exactly identify where this mapping takes. Because if W1, W2, Wn is going to take value with probability 1 in a particular region in Rn, its transformation will take value with probability 1 only in some particular region Rn. Will not be the whole of Rn. Need not be. And since it is a non-singular linear transformation, in general, it will not be. Okay. Yeah, note it down. And please do not neglect this verification. I presume we might have done similar kind of exercises in the two-dimensional case when the mapping involved is a rotation and things like that. And the random variable concerned do not take value in the whole of R2. Okay. So by the appropriate results appealing to that, whose numbers are all given here, and denote A underline denote this A1, A2, An. So F sub A at A1, A2, An is F sub W, underline W, A1 at A1, comma A1 plus A2, comma A1 plus A2 plus An, if all the AIs are positive. If all the AIs are strictly positive, note that A1, of course, A1 is positive. A1 is strictly less than A1 plus A2, and which will be strictly less than A1 plus A2 plus A3, and so on. That will be less than A1 plus A2 plus An. That is finite, of course. So, if these AIs belong to the orthant, positive orthant, this guy belongs to the GM. And of course, then you write down the formula for this. That is, you know that lambda power n multiplied with e to the power minus lambda A1 plus A2 plus An. And that you can easily split like this. So the joint density of F sub A at A1, A2, AN is lambda times e to the power minus lambda times e to the power minus lambda A1 multiplied with lambda times e to the power minus lambda A2, etc. And it is 0 outside of this orthogonal. And this result, this bullet sub n, that's what this expression, this holds for every n. And here note that if this happens, immediately this expression gives you that A1, A2, AN are all independent random variables. And each of them has an exponential distribution with parameter lambda. So since this dangerous sounding name we have given, bullet sub n, holds for every n, we have the following result. So n is the time homogeneous Poisson process with arrival rate lambda. A1, A2 dot 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 are the inter-arrival times. Then A1, A2, etc. is a sequence of independent, identically distributed random variables, each having an exponential distribution with parameter lambda. So now you sort of see the connection between homogeneous Poisson process and the exponential distribution. Yeah. So please note it down. So when n equal to 3 and 4, please check all those arguments. And what we have here is a fairly rigorous way of doing it. So yeah, simple example. I'm not going to prove anything here. So let us say, one of the kind of instances where Poisson process has been observed to be useful is when you have a system or a device which is subject to certain shocks, which are random. And assume that shocks to a device happen. Maybe in electrical devices, there could be sudden surge, or mechanical devices, there could be some kind of a lateral pressure or thrust and things like that. So these shocks happen according to a time homogeneous Poisson process n with arrival rate lambda. So very often these devices may also be built strong enough so that they withstand the shocks, but perhaps only up to a point. Maybe they can withstand about 1,000 shocks, but beyond that, that might fail. So let's say the device fails due to the cumulative effect of K shocks. So let capital D denote the lifetime of the device. So what's the distribution of capital T? Observe that if we have to transform this into our jargon, this T will be precisely WK, the arrival time of the kth shock. So the distribution of T, the distribution of the lifetime in this case, is precisely the distribution of WK, which you can find as an exercise. It will also be an exercise in the problem set I will be giving soon. So we will stop here for the day. If you want me to go back to any of these slides of this discussion concerning inter-arrival times and so on, we can do it. Okay, then now we will stop sharing. And yeah, so that side kind of finishes the discussion on this. So this I will upload perhaps today itself. Maybe one error, typo I have to correct. And the next class we will take up conditional distribution of the arrival times. That might also involve, by the way, have you people done order statistics in your earlier course?
Yes, sir.
In probability?
Yes, sir.
Okay, but anyway, that you will have done in the context of continuous random variables?
Yes.
Okay, so that makes my job simple, because that is one thing where dealing with the continuous random variables is simpler than discrete random. In general, discrete random variables are simpler, but order statistics is one aspect where continuous random variables are simple. So that portion, that order statistics, that discussion, I will do it, and that I will read this thing that we will follow Hoyle-Portenstone probability theory. Yeah. So if there are no further queries, we will, or in any comments, we will stop here for the day. Okay.
Thank you, sir.
Yeah. Thank you very much and take care.
Thank you, sir.
We'll see you on Friday.